So then I would say we start.
I guess, but are two people missing? Because for the research topics, 27 people signed up, and now we are 27 people here, including two of us.
Okay. Yeah, but maybe they are late, or we will see. So we start with a group that is
machine learning.
Can you show the slide where we see the different topics?
I have my Moodle page on here. I can show it.
Or the Moodle page.
Here.
Okay, so today we have our presentation session. This is kind of cool because each of the groups became somehow an expert in a specific topic. And we're really looking forward to see what you figured out. And so on both sides, what is the background on a specific methodology or specific technology, and how we can make use of that in Grasshopper. So I would say is the first group here, the machine learning and artificial neural networks group.
With Chen, Liu Bo, Tao, Mikhail, and Bibo.
Yeah, you have to say if you are here.
Yeah.
One is here?
Yeah.
Okay, perfect. Then let's start.
Okay.
So you please share your slides and then you can start. Who shares the slides? Yeah.
Can you see my slides now?
Yeah.
Okay, so we are the machine learning and artificial neural networks group, and I'm Wenju. So first, I will give general introduction or definition of neural networks. So this is a very famous meme of deep learning. So this is what society thinks I do, and this is what my friends think I do, and this is what actually I'm doing with deep learning. So what exactly is neural networks or machine learning? So machine learning is like looking for a good function, and we input the data and we hope that the computer can give us an output we want. For example, for speech recognition, we just input a piece of audio in this function, and we hope that computer can tell us that it's how are you. And as for image classification, we put a picture of this into the function, and we hope that computer can recognize it and tells us that this is a dog. So next part, I will briefly introduce 3 steps of machine learning. Steps 1 is we have a function, or as we call it, a neural network with some unknown parameter. And we have a lot of data, which I said that is label data but for some of the cases or some of the neural networks, the data are not labeled, but we are not discuss this here. So just assume that the data is labeled, and which means that we will give computer some pictures like this and tell the computer that this is a dog, and we give computer another picture and tell it again this is a dog. And next time we hope that when computer sees a picture of dog, and it will recognize it and tell us that, oh, this is a dog. So the first part, we have our model, and the step 2 is define laws, which in this step, we are kind of define a method to evaluate if our model is good or bad. So for example, for these two pictures, the black line is the target, which is the correct answer. Just like this, dog are the correct answers. And the green and red dots are what computer predict. So in this picture, the red dot is not too far from the black line, which is the correct answer. But this one, the green dots are more far away from the correct answer. So in this method, we can define that this model is better. So we find a way to evaluate our model. And the next step, we just automate it to make the prediction more precise. And as for this, the step 1, the neural networks, I'm going to introduce 2 kinds of neural networks architecture, which my teammates will further introduce how to apply them on architecture. So this is just a brief introduction. So the first one is classification. And this one is kind of straightforward. So I just give an example to easier understand. So the example is medical diagnosis. And we just input some substance, age, gender into this function, or it's called neural network, and output which kind of disease you have. So this is how classification works. And the next one is called generative adversarial network, also known as GAN. This one is a little more complicated. So apart from just input into a network and get an output, this one we actually add a random noise. So why do we do that? So this network is especially for text that needs creativity. For example, if we tell the computer to draw an apple, if we don't, we will do it without random noise, the computer will output the same apple every time, which is boring. So if we add a random noise, that means that the first apple will differ from the second one and the third one because it's random, right? So it's kind of good for creativity. Okay, so that's about my part. And I'll pass to the next one.
Yes, okay. I think I'll start demonstration further because I need some GIFs in my presentation. So you can see my screen. Yes?
Yes.
Okay. So like the first, we can say that when we're talking about architecture, there is 2 main fields like to how to use it, and it's analysis and generation. So analysis is to analyze something that we already have, and generation to create something new. The first one is classification. For example, when we can use it for maps analysis, like to classificate where is the roads, where is the building, to use this information further for our researches. And it's really useful when we can get the satellite photos to recognize all these objects and not do it manually. Another way is to find some features. For example, we can use the street Google views to walk on the streets and to recognize some specific features of the building and to connect them with, for example, the construction date. And here is the map with the age of the building. I'm not really sure that it's made with the neural networks, because I think that we can get some information like from the GIS, but we can also add this information, for example, like these maps, like green canopy in the cities. So this project is about we can compare some cities because we have these maps with the green canopies that are pointed on the map. And it was made with the using of the Google Street Views, so we can walk there to recognize how much greenery we have. And it's really important, for example, that we can make it from the human perception, like not on the map from the upwards to see how it looks like, but when we are walking. Because when we are talking about comfort in the city, it's really important to think about the people that are living in the cities, and from their perspective, analyze these cities. We can also classificate the like frontage classes. For example, we can divide it into 4 categories, like blank frontages, single active, buff active, and non-urban frontages, because it's also important for perception of the people that are walking there, because it's really more nice when you have some active front on the street. And we can put it also on the map and analyze where the conditions are good and where it's bad. Another example of classification is this suggested cut. It can help us to make our 3D modeling. Like when we are starting to model some object, a neural network can predict what are we going to make. So the first step is to classify what is it, what kind of furniture, yes, what kind of furniture it is, like it's a table or a chair. And when we have a library of 3D models, the next step would be to suggest us some examples that we can already use. So you can spend not so much time for modeling because you only start to model, and then you can choose some option that suits you good. Another way to use neural nets is prediction. For example, now we have these new materials that are thermoactive and they can change their forms, but it's really difficult to predict the behavior of these materials. And that's why we can learn our neural network to make this prediction. Like for the input, we need some example like the experiments. So we can put different patterns and watch the results. And then neural network can learn to predict. And the next time we can just give her like in the results that we want to become. And she will set us what the cutout pattern do we need to get this form. For example, for difficult facades, we can use it to get this form that we want. And the second field, like the generation, here we can see the process of the training of the neural network. So the first thing that she produced is not really look like a plans, but then it's possible to teach her how to provide us good plans for our buildings. And there's also some steps, like we can put the parcel of our parcel and to get some counter for our building, then some sketch of the plan, and then the more detailed plan with the furniture. It's also possible to make some specific cases, like when you already know some location of the room and you want to save it, you can put this information into a net. So, for example, this here the bedroom, like she will be on this. It will be on this place, and other will be random. Or when we already have some net with the construction, we can also put it to the neural network, and she will consider this information. It's also possible to generate facades. Actually, they not really look good, but I think that it's also another possibility to use networks for architecture. Yes, and then another part.
Okay. Yes, my part. I'll share my screen, so maybe you can close your screen.
Yeah.
Okay. Okay, my part is about, first I will introduce some interdisciplinary transformation and combination. First, we see some pictures of landmarks in
Can you do full screen, please?
It's my first time to use that, and I don't know how.
Here, present on the right upper corner.
Where?
Next to the yellow button, share. Right, on the right border of the screen. No, go to the right border of the screen.
This. Okay.
Yeah.
Okay. And it helps architect to bring more inspiration from other disciplines, like you can find some painting and some like sculpture, and you can combine this together like this. And I think yes, I think it's what machine learning in this part do is to make it more plausible that you can machine learning can find the edge and the window and the doors, and yeah, that's not a picture on another picture. It's a good combination, and it can also use the good on in 3D. And if you regulating the influence of machine learning, and you can see more performance of urban and building. So another example, I name it humanization, because I think machine learning is not only analyze the building or the road or urban, it can also analyze the people's thinking and behavior, I think. So another example I will introduce is a design, how machine learning help the architecture to design more faster and easier, because it will help the architect to select some preference and give it to architecture. So yes. Another is a behavior analyze. You can see the machine learning can capture the behavior happened in a space and collect them, then help the architect to improve the quality of the space and make the space more easier to use. And yes, I think that is quite useful. And another I want to, and it's quite important, I think, is building safety first. And you can see some cameras surrounding the job site. And if the designer input some pictures that of accident happened before, and the computer will analyze and figure out some similarities, and when the cameras around the job site take some pictures, and it will analyze in real time some safety risk and of the job site, and it will ensure the work's life safety. I think is quite important. Another is a lace wall. I like this project, and I think it's quite interesting. You can see there are some small modules. They are quite interdependent, and if you see that what machine learning do, actually there's many other computer knowledges, not only machine learning, but I think machine learning helps a lot, and it can simulate the H-of generation structure and maybe analyze the false conditions, and next combine the small models together, and it will help architecture to create more stable structures. And yes, I think that is what machine learning do. So maybe next is some introduction to plugins. Yes.
Okay, then I think I'm going to share my screen. But the thing is, my laptop doesn't have a webcam, so even if I share my screen, you might not able to see me because I'm providing the video feed through my phone. Moment here. Sorry. So after like the other members of our group has introduced you to the different definitions and possibilities that some application that are already in use of machine learning. Now let's take a step back and more focus on the Grasshopper platform, which is the tools that we're going to be utilized a lot at the end. In order to go further, though, I think it's important for us to have a short recap about some important definitions because, obviously the presentation has gotten quite long with a lot of information. So in order to reduce some confusing, I'd like to repeat some very important definitions. For example, the machine learning is more about prediction instead of those traditional linear rule-based simulations. So in order to predict, we would have to use historic data to train a model so that we could predict with new data, like to test data, so to say. So a very commonly used data type in the industry is called the tensor. The nature of machine learning is basic matrix calculation. So tensor is a algebraic object that described a multilinear relationship between sets of algebraic objects related to a vector space. So they are like vectors or sets of vectors. So under this category, there are two schools, I would say, learning. The first one is supervised learning, and the second one is unsupervised. The main difference is that supervised learning is a process where you train the model with labels. For example, I have a pen here. I put this into the model and saying that it's a pen and this is a mouse. So they are all labeled. It will achieve a more precise training result. And the unsupervised learning is basically you put all those different objects into it without telling the algorithm what they are, and they'll try to analyze and cluster unlabeled data and try to discover hidden patterns in data, so to say. Under supervised learning, the two mostly commonly used purpose are, as the examples showed, some classification and regression. And on the unsupervised learning, and as you said, it makes sense. If nothing is labeled, they will try to cluster. Like clustering is a use of unsupervised learning, where they try to cluster different objects through their similarities and differences. And then another use of unclustered learning, unsupervised learning is association, to find the underlying patterns, so to say. And then also, if the data set is too big, in order to maintain the model integrity, it would have to reduce the dimension. It's called the dimensionality reduction. It's also one of the signature use of unsupervised learning. So after our research, there are 4 Grasshopper plugin that caught our attention, which utilize machine learning or powered by machine learning. First one is Launchbox ML. It's a I would say it's a nice to have. It's an extraness out of the very famous Launchbox plugin. And then the owl and ant and doodoo, somehow either animals and insect named. So let's get into those interfaces and have a look what they have to offer. This is Launchbox. Actually, when you install Launchbox, this Launchbox ML section was also automatically being installed into your Grasshopper. You can see there's like a use of regression, which is supervised learning. And then there are also clustering, which are unsupervised learning. So with those trainer and tester, we are able to train either unsupervised and supervised model. But you see, this is actually just a small section. So when we look at the next one, which is the OWL plugin, it has 3 sets of tools that we can utilize. And you may see here in the OWL tab, there are like tons of different tools. For example, you can convert data trees to tensor sets, and you can display the result, and also IO, input output component, and some image processing components, and then the whole rest of the section of the OWL tab are the tools that you can manipulate tensor data type. And then if you go onto the OWL Accord tab, there are this is a learning algorithm called backpropagation, and then the display component, and also networks. And there are also, when you go down to the OWL Learning tab, you have the possibility to define supervised and unsupervised learning process. The next one, Ant, is the one that uses a different library, so to say. It has the dependency of a so-called scikit-learn library. It has the possibility to get the input from different data types like CSV, like digital data sets, also Excel form as input. And then it has more like a it also has supervised and unsupervised possibilities. And then the Doodoo is one of the earliest Grasshopper plugin that is powered by machine learning. But it's very, it was in a very beginning stage with not a lot of possibilities or functionalities. It features neural networks, gradient descent, swarm optimization, and it also has like those tools for scalar vectors, tensor field, and tensor manipulation, and it'll use those curvature field as like use ISO surfaces to visualize the result. And then we can have a look at the comparison between those plugins. One important thing for us is to know which one for us is the one that we could actually benefit from. So the first step I've done is to test out the compatibilities of those plugins, because apparently some is already outdated. Oh, sorry, my Siri was waking up. And the Launchbox ML is, I think it's the latest one, because the Launchbox has continuously been support. So it has the latest support for Rhino 7. And then the L, it only has official support up to Rhino 6, but after testing, it's also operable on Rhino 7. The next one, Doodle, it's, as said, it's the earliest one, but it's also the earliest one that got discontinued. It only got support up to Rhino 5, and it malfunctions on Rhino 7 after testing. And then the ANT, the last update of ANT is 4 years ago. It's all from one single developer, which basically developed this tool for a paper. It's open source, but apparently after this paper being published, he doesn't have some motivation anymore to get it up to date. So, and it also has the dependent of this scikit-learn library. Even if I set up the environment, it doesn't work in any extent on Rhino 7. So those last two are discontinued. We're more focused on the first, both. So it's very funny that all, like both plug-in machine learning algorithm, like they all use the AccordNet library, but they have different weighting into their philosophy. So say for Launchbox ML, the machine learning part is more like a cherry on top to the classic Launchbox functionalities. It's just something they added to the Launchbox. And the L is like a dedicated machine learning component plugin. All the functions are about machine learning. So as we said, like we've just watched the different components on the in the Grasshopper. In Launchbox ML, you have a feeling that is the selection of tools and components are more concise, simplified, and user-friendlier. And one important thing that the Launchbox ML has for like different learning algorithm that is possible for us to train the model. The first one is back propagation, and then the resilient back propagation. The third one is called evolutionary genetic algorithm, and then the last one is Liebenberg-Marquardt learning algorithm. But as for the L plugin, it has extensive range of tools for machine learning. Especially, we can very precisely, like very universally have the control of tensor or tensor sets. But it seems like the only available learning algorithm that we can use is the back propagation. In that part is a little bit limited, but as those two plugins based on the same machine learning framework or library, we could kind of expect similar results from both of them. Yeah, okay, then now pass this on to
Tao, yes, you may continue showing. I will just briefly
okay,
show some
just tell
examples.
me to change the slide.
Yeah, just two slides, okay. Just two examples of briefly how it works. So we how can the algorithm learn what to do? We give him a cloud of points, for instance, and now he must turn it into maths. So somehow understand what numerical sense does this point cloud have. He understands that yes, we can make the deconstruct component and say each point has its x and y coordinate. So it understands the logic. If x is that big, the y is this. If x is bigger, then y changes and it becomes smaller, or I don't know. So it kind of understands the logic, and if yes, and the logic, the raw logic without any implementation of the knowledge, it's just a curve which connects all these points. So it's very, very curvy, and well, there is simply just he understands what is happening in terms of coordinates. And could you please show another slide? The next. So if we just connect simply them, it will be a usual curve. And then we ask the algorithm. So you got the point, you got the logic of how it's now organized. Could you please predict, just try to rack your brain and predict what if this cloud would be, what if it was more moderate? What if points were closer to each other, but it's not certainly clear how we can do it. So it's not a usual algorithm where we say, if this point is higher, we put it lower. If it is lower, we put it higher. No, here it's very unclear how it should be predicted. So the machine itself tries to predict it, and the parameter is the amount of how hard the machine should think. So how many iterations of its, thinking should be used. And finally, it creates an almost even curve, which, well, is a calibrated original curve. So that's a very interesting process because, yeah, and the second example also can cover, could you please show the next slide? Yeah, and here just about, again, the prediction, if we have, for instance, and about the classification. If we have some kind of characteristics of shape, for instance, the area or the perimeter or the planarity, I don't know, we can add as many characteristics as possible into the solution, yeah? So it analyzes the given data, the training data, in terms of these characteristics. So it looks at this. How many angles does it have if we put this? What is the area? What is the perimeter length, planarity, and stuff. And finally, we give him the set of our shapes, and we tell him, please decide how to classify them. I mean, to which domain do they belong? Is this a square or is this a planar surface, whatever? I mean, and the parameter again is how hard it thinks, how many iterations it makes in order to predict it. And we can even see what is the percentage of the probability of his solutions. So if we place like 10 iterations, it's very hard thinking. So it really, I mean, thinks very good. And in the end, we can put the panel and see that the probability of this classification is 82%. So it's almost 100, but not very perfect. Okay, he tried, but there are some, I mean, better variations, but he needs to think more. So that's like simply in a nutshell how the Lunchbox ML might work. So of course we can make more complicated and complex ideas and logics, but it's like the very, very simple way.
Sorry, you really need to speed up a bit.
Yeah. So that's all. I mean, that's the end. Yeah.
Speed up.
We've
That's the
deleted,
end.
yes, the other 100 slides, and now that's it.
Okay, thank you very much. Are there any questions from the audience? They're kind of flashed.
Maybe you can stop sharing your screen so we can see each other. Or
Yeah.
yeah. If no one has a question, I actually have something in mind. I don't know how much you were discussing with within the group mates, but to combine all of them. So I think Lyubo and Bibo showed some examples. If you would combine this, what others were talking about, such as the logic that Michael was talking about, like the machine learning is recognizing where are the streets, where are the buildings, what kind of parameters are in there. So like what did the urban planners or architects define as the parameters so that the machine learning could understand, and which plugins that Tao explained could be used in which example. Do you have anything in mind and say, yeah, to combine all of them, this could be an example?
You mean make it more precise to architecture? I mean, connect.
Yeah, for example, that project that the machine learning was recognizing when looked at a satellite picture, it could see which one was the buildings and which one was the street. And you mentioned like what kind of parameters that they were looking at. If it's like shapes, they were looking at the areas and the corners. And if it's like a whole city, what kind of parameters it could look at to recognize what is which, and which plugin could be used to achieve that goal. But mine is just out of curiosity. You didn't have to think about that.
Okay.
I have something general. I thought it was very interesting, and I think it was a good mix. For me, I would have the wish to show a bit more what the plugins are doing, because when you show just the text or your table, nobody here has an imagination what it can do. So Tao, you're very deep in the topic grasshopper already. So in a case like this, you really need to go one step back and think about how can I show people that have no idea about that what it can do. The other thing is when you present something, especially via Zoom or so, you really need to show us input. When there's a slide like the last one where we have the same 5 words for 5 minutes, the people will draft away because we can't see your gestures and we can't see your mimic in the way it would be like when you do it as a presentation or as a real presentation. Yeah, but cool. I think this was a good overview. You are now our experts in machine learning, deep learning, and all these things. And if there are questions because people want to use things like that, they will pop up and will ask how you can, if you have some input from them. Okay, thank you very much. Then we switch to the next group. That was Elida.
Physics simulation.
Yes, physics simulation.
Physics
Okay,
simulation.
I will share my screen. Just one. Okay, and make it. So, good morning, everyone. We are Madeleine, David, Yuxing, Adrian, and Feng Fei. And our topic is physics simulation, structure simulation, and topology optimization. At first, I will tell you some general definition. Physics simulation is the recreation of a real-world occurrence. And then structural simulation is the development of mathematical models that describe the behavior of structural materials, components, and systems. And the last one, topology optimization. At first, this is topology is a Greek word, and it means location. And topology optimization is a mathematical method that optimizes material layout within a given space for a given set of loads, boundary conditions, and constraints with the goal of maximizing the performance of the system. And then we have make a diagram to show how the simulation works. At first, we will give some information such as process geometry, material properties, realistic representation of physical and natural process, and also rational predictions as input. We will give all this data to a plugin or a platform, and this program will do the realistic simulations. And as a result, we could do some innovative designs, optimal functionality, ensure safety, and safeguard sustainability for ecology. And we will show you some example in the further sliders. Yeah, and this simulation is always used like a method to solve industry challenges because of the changes during construction. It causes cost overruns or delay for the project. And if we want to achieve the balance between cost, time, and quality, we could use those simulations as a tool, and we could also achieve the balance between profitable, sustainable, and safe. And this picture shows one a construction project based on this structural simulation. Yeah, and then we will tell you more details about each subtopics. Yeah. Should I go and share my screen, or would you go on,
No,
Madeline?
it's thanks. Maybe I will just tell you when you can.
Okay. Yeah.
I'm going to present you some basic information about physical simulations and give you some examples. So in principle, it's a numerical optimization method to optimize a design, especially in regards to physical influences and externalities such as wind, rain, heat, or also like the shading function of surrounding materials or such as buildings or trees. This is done in order to measure, for example, the thermal performance, in order to guarantee thermal comfort and also like a well-functioning building envelope. Currently, this is already done, but more simplified with more linear calculation models, which are, for example, implemented in the NF simulations, or like NF is the Einsparverordnung, where you can calculate like the energy demand for a building, but it's very linear. And modern simulation tools can be used to calculate it more precisely and depict it more realistically. The main goal is, for example, to reduce the energy demand in buildings through the optimal design. And this energy demand refers to, for example, heating, cooling, ventilation in buildings, and so on. And by choosing the optimal design of a building envelope, the energy demand can be reduced. for example, using parametric energy simulations already in the early design stages. So this is quite important because the design of a building is in direct relation to physical influences. As you can see on the right, there's a picture with a room with different window sizes, and on the diagrams on the right are depicting how much light is entering in the room. And it's a very simple thing to think about. So you have a big window, so you have a lot of light, but in the same time, you have more solar heat gains. And this can either lead to the optimal use of the solar gains and reduce the energy demand, or it can also increase or lead to overheating in the room. So this is just to give you an idea about how these tools can be used in order to find out what's the optimal size of the window in order to have sufficient daylight, but also reduce the energy demand to an optimal degree. But we will give you some more examples for that. Just to give you an idea what kind of plugins can be used. Those are usually Honeybee, Ladybug, Transys, IDEs, but also Ansys. And yeah, required data are usually climate data. So on the next slide, you can see an example how the daylight use was optimized in the Sächsische Aufbank Leipzig, which was a collaboration of ACME architects and Transolar, and they have this courtyard like forest, how you can say. So they have like 251 beams, kind of create a forest made out of beams. And the idea of Transolar was to see, okay, how much daylight can we get into our rooms and how many beams do we need for that, or how many beams, what is too much and what's too many. So they did some simulations where they have a baseline scenario with a lot of beams, then they reduced the beams, and then they also created some atriums. So where like not everything covered with those tree-like beams, but they also cut some holes in it. And then they analyzed the outcome of that. For that, they used the plugin Honeybee, but other possible softwares that can be used for daylight analysis are IDEs or Relux, but also several programs like Revit can already do daylight analysis. Slide, you can see the Harvard Science Center and Engineering Complex, also done in collaboration with Transolar, and here they developed a parametric facade in order to find out what's the best amount of covered parts of the windows in order to guarantee sufficient daylight in the interior, but also avoid overheating and reduce energy demand by guaranteeing an optimal thermal comfort. And what they did is they have this external shading device, which has different types of openings and angles. So the sunlight is reflected inside or reflected to the outside. Yeah, and they also, I don't know which kind of plugins they use, but I also assume they use Ladybug and Honeybee to work with that, because yeah. On the next slide, my colleague David is going to explain about it.
Yes, so in this example, they try to eliminate calm zones between these buildings to utilize the natural ventilation, and they simulated the airflow, as you can see on the pictures on the right. The red dotted lines are the places that were changed during the optimization. So they changed the position and sizes of different windows and doors. And the goal was to reduce these blue areas between the buildings. And on the bottom right, you can see that there is very little of these calm zones as the result of this optimization. And on the next slide, they try to maximize the wind speed on the top of high-rise buildings to utilize it with wind turbines. And they run a lot of simulations. For example, they tried the different roof edges. As you can see, these 4 variants. And on the right, this is the result they got from the simulation. For these, they use the Autodesk computational fluid dynamics. And I think the downside of this program is that it is only capable of simulation, and it is not optimizing the shape of the buildings. So it is a trial and error process.
Here just gathered again what kind of softwares and plugins can be used and what, for example, Ladybug can do. So they have like a, sorry, somebody's ringing the doorbell. They have to wait. Yeah, for example, Ladybug can do climate, data plots, or some path graphics. So there's a lot of stuff that they can do. Really have the time to explain it in precisely because every of those programs probably need like an own introduction. But I just wanted to highlight again that the design of a building is in direct relation to physical influences. So yeah, it really defines how the building is shaped, for example, with geometry. And then I will hand over to Adrian, who's explaining the next part. Thank you.
Yeah, next slide, please. So yeah, I'm going to talk about the structural simulation and especially the topology optimization. Those two topics are linked together quite well. I want to introduce with basically the pre-computer form of structural simulation, which, for example, Frei Otto did for the Olympia Park, which we all know, but also the Multihalle Mannheim, where you can see the model on the right side, like this hanging model. So it was also possible to stimulate structures or like minimal surfaces with the SOAP model before the computer was invented. And so on the next slide, you can see that behind all those things you can find out by using a model, there's also a mathematical calculation behind it, obviously. And David explained this to us yesterday. So how this minimal surface is going to be calculated. And yeah, now obviously computer programs easily can handle those formulas in fast speed and in high amounts. So yeah, next slide, please. And once geometries become very complex, like engines or other components of technical products, there is one method which is very useful to calculate all this. It's called the finite element method. And it basically breaks down those complex geometries into small, easy to handle shapes or geometries. And on the next slide, you can basically see how this how the steps are done. So the program takes the geometry. In this case, it's just this square thing, but imagine it to be a complex geometry. It breaks it down into very small elements, like a mesh, or in small squared volumes, basically. And those volumes or squares are all calculated separately or element-wise. And then again, once the calculation is done for those, they are put back together. And the forces which are transferred from one to another element are calculated through the whole component via the nodes between those elements. And with that, you can do a structural simulation of almost any complex or less complex component. Next slide, please. So, and that brings us to the topology optimization, because it basically uses the same technique. So, it's an optimization method, which the topology optimization is an optimization method which calculates the optimal material distribution within a given boundary. It's the example you can see on the, it's the lowest example here, where you have just this squared massive beam, and the topology optimization really starts in several steps. It's an iterative process where the material has to be distributed to make to have an equal stress on each part of the structure, and there is no material wasted within the structure which is not stressed at the full stress, basically. Two other optimization methods is the sizing optimization, for example. It's the most simple one, I'd say. For this one, you also don't need the finite element method. You can calculate it manually or also take programs to do this with these formulas. It's, for example, just the sizing of the truss component. And the other one is the shape optimization, like that in the middle one where you optimize within an already predefined shape or component, how to optimize the material distribution within this. And yeah, the next slide. You see an example how this topology optimization works. It's a chair in this case, done by two Germans. They started just with this very simple shape you can see on the left where this little human sits. So it's basically an ergonomic form for sitting, but it's just a massive block, and they wanted to reduce the material use as much as possible for this chair, and for this they use the finite element software to further reduce the material which is necessary to transfer the forces from the human to the floor, but still keep this ergonomical shape of the chair. And so yeah, exactly. In a lot of steps, it is calculated down, and the material is reduced further and further at spots or in the areas where it's not stressed a lot. So on the next slide, you can see another example. It's a very experimental pavilion, I'd say. It's made out of carbon fiber, and also for this they first of all they can't use the finite element method to calculate the single components, and then they came up with a very innovative construction method, because as you also could see with a chair, it can only be with a 3D print. It's not like simple wood connections or whatever. It's a very complex shape that comes out of those processes. So you need to come up with new manufacturing methods. In this case, it was this kind of weaving or wickeln, I don't know the English term, of carbon fiber strings around predefined shape, but out of the finite element method, they could know where they need more carbon fiber and where they could reduce the amount of carbon fiber. So yeah, so those are the models. Next slide, please.
Yeah, then we will show you another example based on a plugin named Caramba 3D for this construction design. In this project, instead of a normal column raster system, they have at first as input put all this. You can see this all these black lines as parametric input, and this plugin will calculate it automatically and to optimize this topology. And in the second step, it will choose the best geometry for this construction, which could which is enough for this whole building, but at the same time with the least material. And based on this result, the architecture office has developed the construction optimized. At first, it will use this V-shape column, and then based on this, the other building components will also developed. And you can see with the colors, the color shows directly if this scale from the column is enough for this location. And also, you can see for almost each location where the force directions and which direction should the columns be. Yeah.
Okay, can you hear me clearly?
Yeah.
Okay, and this example named nesting building is we just focus on its roof and named the smart slab. And from the picture in the right side, we can see the overall computational design process uses the structural grid as a starting point to generate a basic mesh geometry. And after several iterations of selective subdivision sequences and the parametric smoothing, the final surface, you can see the next slide. The final surface is defined with around 30 million mesh faces, and the overall geometry is structurally optimized for its load case. The material is distributed in a hierarchical grid of curved ribs, so consequently, the overall slab has a weight reduction of nearly 70% in comparison to a conventional concrete slab. And from the next slide, we can see another example. Yeah, genau. And that is Akutagawa West Side office building. And we also focus on the design of the braced frames on the facade of the building. These frames, where optimized, can resist the vertical load of self-weight, also the horizontal seismic force at each floor level. And the frames are required fairly complex formwork to build. So even the material efficiency achieved through the use of topology optimization, but the complexity of the overall construction also increased. So it is reasonable to assume that this would have been a limiting factor on a larger scaled building, but I think with the development of the 3D printing technology, we can solve this kind of problem. And the next, that is the example of Shanghai Himalaya Museum. Actually, like the cases before, that is also the classical typology optimization operation. And we also focus on the building's sculptural exterior, which features organic and evenly carved facade. But another point that we want to emphasize is the utilization of the plugin Millipede. We can see the picture in the middle bottom. By using this kind of plugin, the overall model could be divided into a certain number of small units. When we add or delete some unit blocks, it will calculate the force that this structure will bear consistently. And finally, it can give an optimal typology model. So we can say the main function of this kind of plugin is structural analysis and optimization, which can perform rapid linear and elastic analysis of frame and shell structure. And the next slide, we also introduce other plugins because we think the Rhino and Grasshopper are still the main tool and method for structure simulation and the topology optimization. And the picture on the right side is the related plugin. Also, according to the difference between these two concepts, we give some general information. For example, for the stimulation, structural stimulation, we can use the SCAN and the SolvePro, also the Beaver, but Beaver is mainly focused on the wooden structure. And also just like the MIDPAD that I have introduced, and the same plugin like the TopOpt and also the Karamba 3D that Yuxin had introduced before. And on the left side, we also list some software that we could use, like the computational fluid dynamics from the AutoCAD desk, and Anumis, also the CGAL Plus and something. Yeah, and that is all. Thanks for listening.
Thank you.
Are there any questions?
Questions?
Yeah.
What about the others? Do you have any questions?
Yeah, I have some questions. Maybe you can share the screen again so I can show you. Or maybe you can show me. I just wanted to know again which add-ons you can use for structural optimization in Grasshopper, because I don't know if all of them are for Grasshopper, are they?
Yeah, actually, as other plugins showed here with icons, only plugins for Grasshopper Rhino. Yeah.
Okay. Okay. So there's few. Yeah.
Yeah.
Okay. Thanks.
Have you tested them?
I have used Karamba 3D before.
Okay.
Yeah, and it's actually very simple. You need to input your demand on construction and what kind of parameter elements you want to use, and it will calculate automatically and show you with the color if this scale is enough and like which point must be stronger. And actually, we have also find a video from this website. It shows better how it works. Moment. Okay. May I show my screen again?
Yeah.
Like here. That's it.
Okay. So I would suggest that you really test some of them. When you show them, it would be cool that you just I think there are examples, and if they are free or there is a demo version, you should really test them to see what's going on.
I also have a question.
Yeah.
Do you know how much background information you need about like physics? Because like we now just saw like the finished product, and if I remember correctly about my first term like static lessons, you have like different mass loads between winter and summer. So how do you know which mass load you actually need in your specific region? So do you need to like the background information for that? Or is there some way that in these plugins, or do you have like with the EPW file that is automatically inputted from your locations? You should say, I have here in this Munich, for example, and then they will automatically say that you need these snow loads, for example.
So I know all those climate data are like very precise from like day to hour to minute. So you can like select the degree of information that you want to include, and then automatically I think it would calculate required mass loads based on the climate data. It depends on what kind of simulations you are doing. So, but to be honest, I've never tried Ladybug or Honeybee myself. So yeah.
I tried it once and I don't know that I have the snow load actually. I don't know. Is there this no load in Veggiebug or Honeybee or in some other EPW files? I'm not sure.
And I think you are not calculating a solution for each day, but you are simply calculated the worst possible situation. So in case there is no? Someone wanted to disagree.
No, you continue.
So I meant that you don't need to know the best solution for each day. You just need to have a solution for the worst possible scenario.
Okay, so I would suggest that we just switch to the next one. So we will have, I think we have 5, or do we have 6 today?
We have 6 groups, and environmental simulations group wanted to present next because they had a class right after.
Yeah,
this one.
no problem.
So now.
Actually, can we also, like group 4, keep it on the schedule, like on the previous schedule, because we have BIM actually running parallelly, and yeah, so it will be nice if we don't get pushed back.
Okay, so is it okay for group 3 to present after group 4?
I mean, if we're within the time of the class,
Okay.
yeah, because
Yeah,
I have a
we
class
will be.
afterwards,
We will. That's why we
so
speed
it's
up.
fine.
Okay, so now it's environmental simulation, or good, share it again. Oh, I might have some issue with internet. I'm really sorry about that.
Maybe one of our group mates can share their screen.
Yeah, maybe one
And
of you
click on
share
it.
the screen because my Google presentation is not working.
Yeah, I will share it.
Okay, thank you. Okay, we see it. So good morning, everyone. We're the group presenting the topic environmental simulation. And I will start with some general information, maybe next slide. I will start with some general information and application of environmental simulation, which will not really refer to architecture. And then Noah will present its relevance to architecture and also computational design. After that, Eski, Huimin, and Luis will introduce some plugins for Grasshopper as examples. Next, please. So in general, simulation means to artificially imitate real-life scenarios, and in this case, it is used as a tool to analyze the system's performance. Speaking specifically about environment, it is a method to analyze and examine the mutual influence between a test object and the environment to which the test object will be possibly, or it is to expect that it will be exposed to this environment during all stages of its whole life cycle. So like transportation, usage, and yeah, mainly transportation and usage. Next, please. So the environmental simulation can take place before design or product development, or during the designing process in order to make some improvements, but also after the product is already finished in order to qualify it for the real world usage and find possible problems before you really use it. The typical fields of application include architecture, civil engineering, electrical engineering, but also aerospace, automobile, and material management, and so on. So this variety of application fields means that the test object can either be a product like a car or a device or something similar to it, a building, or even living systems like a plant or insects. So the test object will be put either digitally or physically into an artificial environment, which contain different conditions or so-called impacts. And these impacts can be like from natural origin or I call them unnatural impacts. So the natural impacts are maybe the climatic ones, and the unnatural impacts include, for example, shock and vibrations during the transportation of the product. With the current technology, it is also possible to simulate some environment in space in order to test, for example, satellite or spaceship equipment and so on. Next, please. Generally speaking, there are 4 steps of environmental simulation. Firstly, the real world environment will be analyzed and the influence will be calculated. After that, it's the simulation. And then the environmental impacts onto the test object will be evaluated. And finally, it is to be examined if there are possible repercussion, which means like the impact from the test object backwards onto the environment. It's a bit like the grasshopper example we did last week. So we see the finished building has some impacts onto its environment. So but in the practice, the environmental simulation not only take places in, like say, in computer, using computer programs like we all know for the building sector. There is also a large variety of equipments in laboratories, which I will show some examples later. So the aims of this environmental simulation is to collect data about a product or building's performance, its operational behavior, but also its long-term behavior, and to estimate its lifespan. And like people want to collect this data as early as possible, like not. It's also helpful for the design process. Next, please. Yeah, this will be the example for the computer-aided simulation, which will be explained with more detail in following pages. Next, please. And this one is a so-called temperature chamber. So the test object will be put into this temperature chamber and to see its behavior, its performance. This temperature chamber can simulate the different temperatures according to climate zones or seasons, and so on. Next, please. And this one is a larger chamber. It's called the rain chamber. This rain chamber is used to test if there is any leaks on this car. So this will be like a testing before the car will go on the market. So basically, we found out that there are many so-called chambers to simulate different environmental impacts. For example, temperature, humidity, altitude, solar radiation, and also over and under pressure, explosive and corrosive atmosphere, and so on. So basically, the product will be tested in a simulated environment with the so-called worst case. So to prove that they are robust and they are durable enough for real-world use. Next, please. And to sum up, there are several advantages of environmental simulation. For example, it helps designer and product developer to make decisions in a very early stage of design or development. One example will be, as we know, the climate responsive architecture. It can also detect problems before real-life application to ensure safety and product quality, which might be difficult for building because we cannot test the building after it's built and like to rebuild it, something like this. Furthermore, it is also repeatable, so one can run the simulation many times always with the same condition after changing the design and to see if the changes make any improvements. Yeah, and also cost and time efficiency. And finally, it can simulate some extreme conditions which will rarely happen in the reality. So to say, to prepare the product for the worst case situation. Nevertheless, we found that there might be some limits of environmental simulation. For example, the user behavior will be hard to simulate and predict, which can lead to, for example, performance gap if we talk about energy consumption in building sector. And also that the simulation is not equal to reality. So if the design is really dependent on simulation, it might cause some risk or some problems in the using phase. Yeah, next.
So I'm going to talk about the relevance to architecture and computational design. And first, next slide, please. And first, some things about environmental simulations and the planning process. So they play an important role in our planning processes of buildings. But as you can see in the three graphs, these simulations usually are used by building services engineers in the phase of the design development when the volume and the basic concept are already set. So that's why these simulation programs often fail to address environmental design in early stages where most energy savings can be made. And these programs should rather be used or should also be used by the planners themselves in early stages where energy savings almost equal the design effort, as you can see in the second graph. A clear understanding of the design problem and the site environmental condition increases the possibility of making environmentally responsive design decisions, as Fai already said, and so early simulations by the planner would enable early design decisions based on the environmental circumstances. Next slide, please. So what are the tools for planners which can be used in these early stages of design? For an environmental design approach, the initial step is to identify critical environmental factors that influence the building design. So environmental data sets needs to be visualized to can assist designers in their decisions, in their decision findings, and to enable the designer to communicate them. So advanced studies are to be integrated within the building geometry and allows the planner to explore the direct relationship between environmental data and the design. And the use of multiple platforms for this issue and for the design and slows down the process, so it brings a lot of advantages to have only one platform which connects basic analysis like weather data analysis, sandpath diagrams, and advanced environmental studies like daylight simulations and energy simulations. Next slide, please. So as an example, as application possibilities for environmental simulations, we see here a project of the National University of Seoul. And in their project, the students are using software tools to simulate different environmental influences on which their design proposal is based. So here we see the plot and the simulations of the solar conditions here. And according to the outcomes, they proposed a massing. And then after that, they simulated more things with this proposed massing and adjusted their design. So on the next slide, we see how they did wind studies, water flow studies, shadow studies, no barrier path studies, and urban network analysis in a bigger scale. Next slide. So in the Rhino Grasshopper environment, we have several tools to use for environmental studies. And the advantage of Grasshopper and Rhino is that you use one model for design and for the analyzing simulations. And when the base geometry is adapted to some simulations, the design model automatically updates. And it also can be linked with the building information modeling, and so can be integrated in like the common workflows of architecture offices. And here you can see some of the plugins for Rhino, like Ladybug for climate visualization and analysis, Honeybee for building energy daylight simulations, Butterfly for airflow modeling, Dragonfly for urban modeling, and Spider for web simulation. And in the following, we will explain more in detail 3 of them.
In this part of the presentation, we would like to introduce plugins. Next, please. First of all, I would like to explain Gecko plugin, which created by Ursula Flick and Thomas Graeber. Next. Basically, if we look at the meaning of the Gecko, we can do geometry modeling, energy analysis, correlation, and optimization. Next, please. Gecko is a set of the components which establish a live link between Rhino Grasshopper and Autodesk Ecotech to export, evaluate, and import. Gecko allows the one of the export and actively cooperate efficiently with another software called Ecotech in order to evaluate one design with the various performance data. Gecko again make it's possible to import the result as a feedback back into Grasshopper. So this feature provides more ease to users. When look at Ecotech is a visual software for architects which enables them to test environmental performance issues and simulate the various environmental and climate conditions in order to design more green and efficient parametric structure. Next, please. Gecko is designed for the early stage of the conceptual design and encourage the play to understand environmental factors and interactions. Next, please. Why it is useful? Ecotech and access the performance data to import the result as a feedback to Grasshopper. This could be done as a single process or looked to improve performance and the design of the building in the context of its environment. The single result of the process could be saving the Rhino in the vertices of the analysis mesh to store data for the later use inside different design approach. Next, please. How we use? First of all, we need to create a geometry and you can attach the edge or mesh. You can see the analysis in here. Grasshopper will begin its analysis, and that point, if you click the export to mesh to Ecotech, you will see the result of the analysis in the Ecotech program. And it helps to process and visualize see the external data. For example, if we consider a case system, you can calculate the daylighting, sun path, shading times of the different floors. That's it.
And the second plugin I will introduce, guys, is the Ladybug. Next. And after you download the EPW weather file in the website, you can use Grasshopper and you can use plugin Ladybug to do some environmental analysis about sun paths or sun radiation or wind blows or something like this before your project. Yeah, next. And firstly, I will give you an example of the sun path analysis to show how it works. The next. And first, you can use the item download EPW weather file to download the file that you want. Next, like you can get a map and you can find the weather data wherever you want, all of the world mostly, and you can download the file. Yeah, next. And after you download the file, and you can use the item like import EPW file, and you can use the file path to link to the file you have downloaded, and you can connect to the import EPW file, and you can see here something like wind speed or wind direction or location or something that's related to the files you have downloaded. Yeah, next. And then like you can find the sun path simulation item here, like yes, next. Like you can connect the location to the location that you have chosen, and you can see there is an analysis period, which means you can input the period of time that you want to analyze. Like you can analyze the some past between the January to March or something like this, and you can use a target to run it. And then next, you can get some past pattern like this. Like I used the site for my last project to show the result of it. Yeah. Next. And also we can use it for the windrows. Like you can find the windrows here, and you can also link the wind direction to the wind direction and wind speed to the speed. And you can use the same period of time linked to the analysis period and to get the result of the windrows in the same site. And next. And beside these two functions, you can also analyze the some radiation or the radiation rows or the view analysis for your site. And these are really commonly used for the like the analysis before your project, or for the situation that you have already get some plans for the project, and you can find which one is better, like which one is more environment friendlier, and you can choose the better one. But the limit of it, I suppose it's up to the calculation. You have to control the shape of the building by yourself also, because if you directly use the result of the calculation, the shape of the building might be a little bit weird. Yeah. Next.
Yeah, I'm going to present the plugin Honeybee, which is, I think, one of the most popular plugins for environmental simulations. How does it work in general? So Rhino and Grasshopper deliver the geometry, so as the 3D model, and environmental data, like, for instance, the EPW file for the weather, and yeah, certain other parameters which are needed for the simulation. The Honeybee components, depending on the use case, are using external simulation engines, such as Energy Plus for energy modeling, or Radiance for daylight studies. And yeah, the components then provide results which then can be visualized by most likely Ladybug components. So yeah, you would use them together in most cases. Why is it so powerful? I think one reason is the huge variety of functions. Yeah, you see, we have overlappings with the physical simulation part from the group before, but we can take a deeper look into a few functions. Yeah, I have two examples for one for the annual daylight studies and one for thermal comfort in the Grasshopper environment. They are both taken from the Ladybug website, where you can download Grasshopper files for each function, and you can modify or just explore them. It's really good to learn Honeybee, I think. In this case, we have a daylight simulation where annual results are created. In the first step, you put a so-called recipe together, which collects the EPW weather file and the area you want to investigate as test points. This recipe then goes into the component where the actual analysis is running. This component also collects the built environment around the area as Honeybee objects. And yeah, then you have some more parameter going into this component, and this generates the measurements you want to see, you want to show, such as daylight autonomy or useful daylight luminance. And these results can then be visualized or analyzed. The second example is for thermal comfort studies. In this case, you get the results to calculate the predicted mean vote. So in this main component in the middle, you have also the input for the EPW weather file and the zone you want to analyze as the honeybee zone, and yeah, some more parameter such as the information on which output you want to get out of the simulation. And at the end, you get the operative temperature, the air temperature, the mean radiant temperature, and the relative humidity. And then you can calculate the PMV out of it. Yeah, last but not least, we want to just mention some more plugins. We didn't go in detail now. So first one is TrendLizard, which is the implementation of transers in the Grasshopper environment. Then we have Beetle, which is to calculate the embodied carbon in early design stages of steel frame buildings. And then there is a tool called Heliotrope Solar. So you can do accurate solar studies there for complex geometries. And then we have Pando, which can calculate the effects of trees for the outdoor comfort, like in terms of cooling potential and water uptake and transpiration. Yeah, that's it from our side. Thank you. If you have questions, you can ask them now for sure.
Okay, thank you very much. Are there any questions? I think this is a topic that somehow is rising and rising and rising. There are everyday new plugins and new informations and new uses for these environmental topics and environmental tools. So I don't know why the focus is so much on that, but it's very interesting and they are very helpful. I have just a general thing to all of you. We will upload all the presentations to Moodle. Before we do that, you really need to reference your pictures and the sources. So if you show pictures and if you say, hey, this is from this project, then you need to reference that. Everything that is on the slide has to be referenced if it's not yours. Just on the side. Aren't there any questions? Everybody's looking so tired. Maybe we do a short break, you get a coffee, and after that we go ahead with the other presentations.
I don't know how long it will be the pause, but two of us in our group need to go to another class.
And your group?
Yeah.
With the next group?
Yeah.
And when do you need to go to the other class?
Now.
Why do you have two classes at the same time?
Usually happens every semester, so it's not rare.
I know, and every semester I have these discussions with students and with the other chairs that this is not doesn't make sense.
Yeah, and I think they are both from the same chair, so yeah.
Yeah, that's possible.
Is it with Atta?
Yes.
Which course is it?
With Atta BIM,
Yes,
BIM project.
exactly. That's why I wanted to have a break because I need to move to the other.
Fine.
You don't need to do BIM. Not today. Maybe tomorrow.
No, I mean I need to move physically.
So okay, but yeah, how can we do it? Can the others do the? Yeah, maybe then you really need to switch. Then we will talk to Atta. Elida, is Atta there? So we will talk to Atta that two. Maybe you just give the name to Elida via chat. That two guys are late, and then we do just 4 minutes break. So everybody can get up, bring in some fresh air, and then we see us in 4 minutes. Then we do the presentation, and then you can head over to other. And he is informed.
Thanks.
Okay, thanks.
Okay, see you. Okay, 4 minutes over. So next group is, are you prepared?
Mm-hmm. Can someone share a screen?
I think Alessandro wanted to.
Mm-hmm.
Yes.
Okay, thanks. Hello, everyone. My group is going to present the evolutionary and genetic algorithms. We will start from the theoretical introduction, then we will speak about the relevance to the architecture and computational design, and then we will present you the Grasshopper plugins, whose way of working was inspired by the mentioned biological or natural processes. Next slide, please. At the beginning, we would like to speak about the purpose of such algorithms, which is optimization. Simply saying, optimization is a process of making something better. When doing optimization, we are changing our input data or the process in order to achieve the optimal result. The result can be a maximum or a minimum value that we would like to consider satisfactory. In this case, in the case of maximum value, we'll be speaking about fitness, which can be associated with the best performance of the result. If our goal is to find the minimum value, we will be speaking about the cost. Those characteristics are the opposite, but both can be the goal of the optimization process. The evolutionary and genetic algorithms are only examples of numerous types of optimization methods. Next slide, please. But before we will explain how they work, we would like to speak a little bit more about what inspired them, so namely the evolution and genetics. Everyone have already heard about the theory of evolution that was created by Charles Darwin. Shortly speaking, it says that all the living organisms have the same ancestors. In the 19th century, Darwin traveled around the world, investigating nature and taking notes on what he saw. In 1858, he published a book on the origin of species, which described his findings. The four most important are: the offspring inherit the characteristics of the parents, what makes the population stable. What was changed can also pass to the next generation. Not all the offspring will survive, and they won't be able to further reproduce. And the inherited characteristics will influence the chances of survival of the offspring. This is what we call the theory of natural selection, so the survival of the fittest that were able to remain alive to the reproduction age. Next slide, please. The beginning of genetics is associated with Gregor Mendel. He was an Austrian scientist and monk. After failing his exams at the University of Vienna, he started working in a monastery garden where he performed pea plants experiment, mixing their characteristics. His works have been published in 1865. Later, the science of genetics evolved, defining, for example, the process of mitosis and meiosis, or finding out about the genetic mutations. While in mitosis process, the next generation bring copies of the previous one. In meiosis, new and unique organisms are being created. They combine characteristics of both parents, being different from both of them and individual. It's exactly what our genetic algorithms will do. With mutations, we can influence the output randomly or methodologically. Next slide, please. Now it's time to focus on the genetic algorithms itself and explain how they work. At the beginning, we need to define the cost function and its parameters, and basing on them, we can create a population of random solutions that, of course, would not be optimal at the starting point. Among the population, the best elements are chosen to be paired. During the crossover, parts of the genomes of both parents' organisms are exchanged in order to create offspring that is a mix of both parents. The next generation can experience mutations that will additionally change the performance of affected representatives. The process repeats itself, creating new generations by mixing the best solutions from the previous ones. On the next slide, we will explain a bit more how exactly it works. On the picture, you can see a mathematical representation of the organisms as a combination of zeros and ones. The chromosomes of the parents can be exchanged by cutting the genome at one or more crossover points. The mutations that can eventually appear afterwards can be done randomly or serve a function of repairing the genome if it ended up outside of the domain. Among the offspring, the fitness or cost performance evaluation has to be made in order to choose the next pairs. There are two most important methods how to do this. The first one is ranking and the second tournament selection. In ranking, each child receives a rank based on its cost or fitness, that grants the further possibility of being selected. In the tournament selection, the children are compared randomly, and then the better ones will survive. Last but not least, the algorithm needs to finally end. A convergence check is defining the algorithm if the algorithm approached a desired solution. Without this, it could run eternally, creating new and new generations. There are three most common ways of defining if the algorithm has already approached the end. The first one, stopping with a fitness value, for example, reaching a value defined by a norm or a code. The second, stopping with a fitness change, for example, reducing the energy intake of a system by a particular value. And the third one, stopping with time, for example, on the 15th generation. It can also be controlled and stopped manually at any time. Next slide. And before Andres will tell you more about the relevance of the genetic algorithms to architecture, I will present a short example that will illustrate why the genetic algorithms can be really useful when looking for optimal solutions to very complex problems. One of those is a well-known traveling salesman problem. It deals with finding the best way to connect a list of cities that a salesman should visit before coming back to his original location. The optimal solution would involve visiting each city only once and without crossing their own path. The difficulty is NP-hard, with the number of possible solutions growing factorial depending on number of the cities. For only 5 cities, there are 120 possible solutions. For 8 cities, more than 40,000. Finding the only one best solution for even more points would require huge computing power. But if we can agree on finding an excellent solution, but not necessarily the best one, then genetic algorithms fits here perfectly. On the picture on the left, there's a map with 20 cities that should be visited by the traveling salesman. If you are curious, I can tell you that it means above 2 quintillion, so 2 billion of billions of possible ways to do this. To solve this problem, a genetic algorithm was used. Here you can see the 15th generation and the simplified way how the offspring was created. The genome contains the order of cities visited, and the parameter that is used to choose the fittest population members is the total length of a road. In this case, there is also mutation included that replaces the parts of the genome if it will find a repetition in the code. This way, the salesman will not visit the same city twice. As you can see, genetic algorithms can be very useful. What are the possible applications in the architecture? Let's hear what Andreas would like to say about this.
So the relevance of evolutionary algorithms to architecture and computational design can be summarized in the following aspects. One of the daily activities and workflows of architects is to create variations of designs and explore different possibilities. With genetic algorithms, many variations can be generated in a short time period, improving the computational design process with the rules and objectives that we have programmed into the algorithm. We can explore alternatives which aren't based on knowledge. The algorithm explores just a wider range of possible solutions which match the selected objectives. As there are many professionals involved in the construction of building, there are also many variables to consider when designing it. The normal workflow is usually powered by humans in an iterative process of coordination between different disciplines, but with multi-objective optimization, these issues could be addressed with the one same algorithm. Unfortunately, this process can be time-consuming and demands of powerful computing capabilities. Some of the applications in architecture for evolutionary algorithms can be in spatial planning to create, for example, generative floor plans, in structural design to optimize the topology of a structure, with perhaps the aim of reducing the amount of materials needed, in increasing the energy efficiency by, for example, optimizing the orientation based on the sun or on the wind, or maybe for developing a stronger architectural concept by analyzing the views and shaping the building to increase them. In the next slide, we can see an example of a running algorithm with use for spatial planning. Here, many variations of apartment sizes are explored with the objective of finding the most efficient use of the space in a given floor area. An exemplary workflow would be to create the geometry parametrically in Grasshopper and use Galapagos to optimize it. The following slide shows us an optimization process, how an optimization process tries to minimize the torsion moments in the represented structure. Using Grasshopper, Caramba, and Galapagos, the best outcome can be searched, as we can see in this animation. Next in the use cases is an optimization of the energy performance of a building. Here, different window sizes and their orientation are tested to find the solution with the less energy consumption. An exemplary workflow could be to use Grasshopper, Galapagos, and Ladybug tools. It is important to say in this case that Ladybug tools utilizes also other softwares outside the native environment of Grasshopper, which increases the computational requirements and the optimization time. This black window, which always appears in the simulation, is actually from Energy Plus, and this means that also, well, Honeybee will reach to these softwares to try to perform the energy simulation. The next example shows also a similar workflow. On this case, the location of different towers are tested, taking several aspects into consideration. Firstly, the location of the towers in the plot is given by a set of rules which can be based on optimal distances to the neighbors, to themselves, and the shading producing by each tower. Afterwards, the views are optimized so that the final product is not 2 or 3 towers facing direct to each other without any privacy. In this case, there are several optimization processes built as a cascade, one after the other. And the last example shows a very similar case, but with a different workflow, with a multi-objective evolutionary algorithm called WALACI. As an illustration to this workflow, we can see in the right-hand side how many different programs could be needed to evaluate different aspects at one time. In the representation to the left, we can see how several parameters are evaluated, like the height, orientation, and overall the shape, to estimate the best performance of multiple objectives, like the solar radiation of the facades, like the views, and the usable floor area. Now in the next slides, we will take a look how 3 of the most used plugins, Galapagos, Octopus, and Biomorph work. Alexandro will start with Galapagos.
Okay, so we will now jump into the first plugin using genetic algorithms, which is called, as Andres said, Galapagos. What we will look at is, first of all, the general definition of the plugin, and then we will explore the inputs and lastly the outputs which can be generated. So Galapagos is a single objective genetic algorithm, which means it can be used for solving single parameter optimization problems. In simple words, this means that the plugin analyzes one parameter, for example, the length of a path, and optimizes it. Despite the fact that it is a single parameter plugin, it is possible to implement multiple parameters, creating functions, but we will see in detail how this works in the upcoming slides. So when we place Galapagos in the Grasshopper interface, we get the possibility to use 2 inputs, the genome and the fitness. We will start by looking at the fitness, which will help us to understand also the role of the genome. As we saw in the introduction, genetic algorithms are essentially derived from the biological process of evolution by natural selection. In fact, in natural evolution, fitness is a very complex concept, and it's not always about the best, strongest, or highest characteristic. In contrary, in evolutionary computing, we can make the fitness be whatever we want. In the case of Galapagos, we need 1 single number as an input for fitness. What the plugin then will do is to maximize or minimize that number. But we can ask ourselves, what is a number in this case? So it's a characteristic, as we said before, for example, the length of a path, which we want in this case to be as low as possible. And as we have seen in the beginning, it is possible to analyze more than 1 characteristic, and so feed Galapagos with a fitness function instead of a single number. In this example, multiple parameters are analyzed for deciding the window to wall ratio of a facade. And of course, daylight and sunlight play the biggest role in this decision, but also the related gained solar energy and the optimal view or the costs of the facade play a role. So the difficulty here is not to define the parameters, but to define their relation, which would result in a much more complex function than the one we see. As we now have defined what fitness is, we will look at the role of the genome. In this visual example, we look at a two-dimensional genome. This means the genome is composed of two characteristics called genes. We have the gene A and gene B, and genes in fact are variables. This means they can change their values. So these two characteristics can be whatever we want. If we take the previous example, they could be the daylight factors and the cost resulting from a certain facade pattern. What we see in the image is a fitness landscape where on the peaks the fitness values are high, whereas in the valleys they are lower. At the beginning of an optimization problem, the solver obviously does not know how the landscape looks like. The solver now populates the fitness landscape with a wide variety of solutions, and different combinations of daylight conditions and costs of the facade are analyzed by Galapagos and placed on the fitness landscape, being defined by a red point. And since we want to maximize the daylight to cost relation, we will look for solutions which are on the peaks. By doing so, we select the fittest individuals and breed them by taking two fit individuals and creating offspring somewhere in between the parents in the solution space. And by repeating that for many generations, we can achieve fitter and fitter solutions. So in order to look at the output now of Galapagos, we will have a look at a very simple example. In this algorithm, we want to find a path from point A to point B without touching the small rectangles, and the path needs to be as short as possible. To do so, we want then to minimize our fitness. By letting the solver run, we observe on the left picture how in an initial phase Galapagos looks for solutions which do not seem optimal, but after a few generations, he already has restricted the solution space to fitter solutions, which can be seen in the right animation. And so after having seen the first genetic plugin, we will look at a few more, as well as at their advantages and disadvantages in comparison with Galapagos.
So let's start with Octopus. Octopus is a multi-objective genetic optimizer, and it was first introduced in 2012 with its latest update in 2018. On the next slide, I will first talk about the multi-objective problem. So why do we need multiple objectives? On the right-hand side, we see a neat example how we can map something into one fitness function, because the insulation thickness corresponds directly to the insulation cost. So our overall goal is here to just minimize the cost. But in some cases, the different objectives are in different search spaces. For instance, as a student, you want to maximize your credits in each semester, but also minimize the difficulty. So to map or to put the actually ECTS getting and also the difficulty of an exam is really, really difficult. Therefore, we can just try to look at them separately and later on combine them in the Pareto optimality, which we will see on the next slide. What does Pareto optimality mean? Generally, it means that you cannot improve one objective anymore without making a different objective worse. If you take, for instance, the point CC of the so-called prisoner's dilemma, it means you have two players, player left and player top. Both committed a crime and now have to decide if they want to confess or to actually defend themselves. If they both confess, each will spend just 1 month in prison. Let's say player one decided to defend himself. Therefore, he can improve himself by not spending any time in prison, but his partner has to spend 4 months in prison. Therefore, his situation gets worse, and therefore we already have a Pareto optimality. The same goes for CD and DC, since both cannot be improved anymore since they have the highest value. Now look at the point -3, -3, that's DD. It can be improved if just both confess. Therefore, we have a non-optimal solution and we can just disregard that. Therefore, we have 3 different solutions that are maybe not the best ones, but at least some sort of thing that we can use to later on for other calculations and let the user decide what is the best for him. If he has to have a higher focus on player 1, higher focus on player 2, or he wants just to get the best of both worlds. So let's continue with the parameters of Octopus itself. A neat thing about Octopus is that it has similar parameters to Galapagos. First of all, we have the genes and the objectives. The genes are like the input parameters, as earlier on the genomes. The objective functions, we need at least 2, since there are multiple objective functions. Also, you need to consider, if you want to use Octopus, that always tries to minimize the result. Therefore, if you have a maximizing function, you have to just multiply it by -1, as earlier on in the prisoner's dilemma example. Later on, please. We have also optional parameters. Those are outputs, also called phenotypes. Why? They're just some results that actually use to show, first of all, the search space. That's the P side, a mesh, just to see how things differ, how things change over time. Also, we have the PS output. That's actually a tree. Every time after each generation, it produces some sort of output, since you can use it for further calculation to visualize how things actually change in terms of objective, but not the search space itself, which helps for further first calculations, but does not provide any further details too much. So what are the advantages of Octopus and the disadvantages? On the next slide. First of all, the advantages. Octopus is all about flexibility. On the bottom, you will see 4 different results, so you have different alternatives depending on your solutions. Also, it has wider range of variants, because early on in the prisoner's dilemma, you first focused on one player, then you had a focus on different player, and then you have like the best of 2 worlds. So therefore, sometimes you cannot have like one solution. Therefore, you get different ones, and that you decide what do you want to take or what's the best for you. For instance, with some other parameters that cannot be put in numerical ways, like how it looks like. Also, one disadvantage is gradient-free optimization on the next slide. So what's gradient-free? First of all, I need to explain what's gradient-based. That's something that's usually used in deep learning, and here we try to create a continuous function and map all the points on this function and use the slope of this one function to get to our optimum. For instance, if it's more flat, we know we can make some bigger steps. And if it's like too steep, we have to use smaller steps in order to go to an optimum. The point is that Octopus is all about flexibility. So in this case, we need to create a continuous function, which is not always possible. For instance, because we have some discrete values or some noisy values, because some measurements were taken wrongly or there's some rounding errors. Therefore, we can go to a gradient-free approach, where we can just take a point as a point and interpret the result as a result. Next slide, please. But the disadvantage of a gradient-free approach is that's already slower. So generally speaking, Octopus is a lot slower. First of all, gradient-free optimization. Also, overall, it needs more generations to get to an optimum, and also each iteration takes more time. How much time? For instance, for 1,000 iterations, Octopus itself needs 50% more time compared to Galapagos. So if you want to use Octopus, you're all about flexibility, but you also need to provide the computational power, and also you need enough time to actually let the optimization run. In the next part, Axel will present Biomorpher.
So now I'm going to talk about Biomorpher. Biomorpher is also similar to Octopus in the way that it's also a multi-objective optimization algorithm. And also, if we see the nodes, they are pretty much the same. In Octopus, you input the genome, the objectives, and the geometry. And in Biomorpher, it's exactly the same. And if we also look at Galapagos, it's basically the same, but in Biomorpher, you input the geometry, because it's a very visual plugin. So that's to see the different variations that we're going to see in the next slide. So the first thing you need to do in Biomorpher in the interface is set up the population size, and then also the mutation probability at the right side in the settings. And then you click go, and Biomorpher groups all the design into 12 different groups. And each of those groups have very similar parameters. And you also have one centroid genome that is the most representative one of those groups. And that's the one that it's going to be displayed in the next tab, in the design tab. So here's where you decide which genome pools or genome groups will make it to the next generation. So next slide, please. So here, for example, we see we selected the second group, the number 2, and then we clicked evolve. And you can also filter where it says design for. You can also filter based on the fitness parameters or performance parameters that you input in the node to decide which ones are more fitted. Like to not only decide based on what you see, but also decide based on the parameters. So yeah, so basically you click the group and then you click evolve, and here you can see the generation 1, the other one was generation 0. And as you can see, they are all pretty similar because they were all based in one group. So of course it makes sense that they are gonna be very similar. Next slide, please. And then what you can also see in the interface of Biomorpher is the history or the evolutionary tree, where you can go back and forth. For example, if you end up with a design that you don't like, or with parameters that are too extreme, or yeah, maybe you just change your opinion, you can go back in the tree, you can reinstate an older pool of genomes, and then start again the process of generating. Next slide, please. And here we can see just a bigger tree. Next slide, please. I'm not going to talk in detail about the process, but basically what the user needs to do is basically the user is the red part of the process, and the only thing that it needs to do is decide if the final design was found, then you enter, and if not, you can reinstate an older population in the design tree, or just manually select the ones you want and then continue with the evolution, with the iteration. And the rest, yeah, is Biomorpher. And here just a quick example of all the nodes that you get with Biomorpher. You can store the information you got after all the generations in those nodes that said internalize these to store data, like the ID nodes and the 0.1 nodes. And that's very useful if you're in a big project with a lot of data, you don't want to lose that data. It took a lot of time to produce it, so this is very useful. Next slide, please. And then here just a quick sum up from all the things. And we talk about Galapagos, Octopus, and Biomorpher, but there are also other evolutionary plugins. For example, Wallacy, Opossum, and Aereo. And the other ones are not so great, I think, but maybe they are still worth it. And Wallacy, of course, is a really nice plugin. And that's it.
Thank you very much. So the guys who need to go, they just fly to Atta. Yeah, cool. Very interesting. What you also showed, I think, just to sum it up a bit, these genetic algorithms, they make always sense the moment when there is not just one optimal solution, when there are kind of a solution space where we are in and where we need to have one or several parameters that need to be abwägen, measured next to one, so next to each other somehow. And there it makes absolutely sense to do it that way. One example, I don't know if it has happened like that, but it could happen like that, is this bird nest in Beijing, where I say, okay, there is a clear structure where there are these beams that hold the whole nest, and then they did you can do this algorithm where you say, okay, the holes shouldn't be too small because then you can't fix it. The hole shouldn't be too big because then you cannot wrap over the plastic thing. So there it makes absolutely sense to do something like this. And at the end, you get what you already said. You get so many different solutions, but they're all somehow erfüllen.
Filling the purpose.
Filling the purpose. Yeah. Thank you. Yeah, cool. Are there any other questions? No, so much information. But this is cool. This was the idea that you just get an input on all these possibilities, but not only from Grasshopper side, but in totals that you see, okay, there is a technology and this could help here and there. That's why we do it. Okay, then do we have one left or two left?
I think we have two left.
Wow, okay, because no, we
and
shift
40
over
minutes.
to the next group. Have fun with Atta. If you're still here, and see you next week for the workshop.
Sorry, a question in between. Are the slides of each group uploaded somewhere?
Yeah, we need to first you need to fix the problem with the sources, with the references, and then you just send it to us and we will put it on Moodle.
Okay, thanks.
Yeah, there is already a place that you can upload.
Ah, okay. Even
So
better.
everyone would have access later to the slides from other group, right?
Yeah.
Okay, great. Because we also have some example videos for those machine learning plugins, so we
Put
could
it all
also
in.
add it. Yeah. Okay.
Yeah.
Okay, so we're going to talk about multi-agent particle system. So this is we're on the group 4. So, okay, quite fast. An overview of what we're going to talk about today. From one side, particle system and multi-agent system. We'll give you a definition, some applications within computational design and architecture, and some plugins related to it. We will compare also these plugins we're going to talk about, and we're going to define a bit how do you differ what's particle system, what multi-agent system, and how they work together. So first, I hope the videos work. So first, particle system definition. So a particle system is a collection of many particles that together represent a fuzzy object, that you can see here on the video. So when we talk about particles, we might refer them as a minimal expression in a 3D representation, such as a dot. And how these dots create like this fuzzy figures. So they do it over a period of time, and they do it within a system, and they might change and move within this time and also die there. Next. So to talk about the particle system, we go a bit deeper, and we will also talk about the single particle that composes this system. So when we define this system, we define a particle with parameters, and the main parameters as position, velocity, acceleration, and lifetime. Depending on the goal of the system, we might add some other features like size, color, transparency, shape, and forces. When we talk about forces, we related them, for example, with gravity. Yeah, so usually particle systems are divided into 2 stages. We see those stages, I guess, nowadays as maybe simultaneously, because from one side we go to this part of create them with an algorithm or coding, but in our case we will do it through Grasshopper and some plugins, and the other part is the rendering part. So when they get more complex, and we need to add some texture, so that will be the second stage of it. So we also brought up this part of the movie Star Trek, because in around 1982, the producers of this film, they tried to recreate this simulation of this visualization of what you're seeing right now. So this is fuzzy visualization to try to take over the planet. So that was the first time where the term particle systems was coined. So since then, in the early 80s, particle systems have been used in countless video games, animation, digital art pieces, installations, to try to recreate these natural phenomena that are difficult to represent, such as fire, smoke, waterfall, fog, grass, bubbles, and so on. So then becomes a useful technique in computer graphics from one side when we now talk about the applications for it. So usually the application is to do visualization of systems. So from one side, we can talk about it as embodied simulations. Embodied simulations are when one particles affect another particle. So they're mainly used to simulate galaxies and to simulate the universe. But what gets complicated with it is that they are computational expensive and use large resources, because when we talk about the universe, we don't say, okay, it's one or two particles, but it's billions, trillions of particles that affect each other. So then it turns a bit dense in terms of resources. And here at the right side, we can see the visualization of the history of the universe. So how it evolves and what are the uses for it. So to recreate things. So another use for it is yes, within the mechanics and fluids simulations. So here we have a smooth particle hydrodynamic, which is a computational method to simulate this mechanics and fluids. So they use it to position-based fluids and use it as for applying it in mechanics. So here at the right side, we see just an example of how they do happen the fluid simulations of a combination of particles. Another application is with mass spring systems. Usually when we talk about this mass spring systems, we relate it with so the particles are connected within springs, and they're influenced by some forces. So that's how we see it on this example on the video. So usually to recreate flow simulation, and it's based on Hooke's law. Okay, so when we talk about the applications architecture, we might also relate it as a visualization application, and as for example, or partners for environmental simulations. So this is quite a basic for dual dot representation. So from one side here we can see an example of a representation of rain, but the particle systems maybe don't go farther. But within the design uses, we might use this data that gives us this visualization for the designing. Let's say in this case, for the surface, how affects it and how can we improve it. So in detail, we can also visualize dust, air pollution, turbulence, gravity, and forces, and also, for example, for thermal comfort, do these visualizations. So also we can do some more specific visualizations that are related with population, buildings, trees, and the particles itself become the agents for multi-agent system, which we'll talk a bit later. So here we can see how this might happen. Then particles then become persons, and then they move. We give them some parameters, so they move along it. So, but the point is that particle systems do the visualization part, but then they come more things with it that just not particle systems. And we figure out that when we combined a particle system with springs, we have these particle spring systems where, what I said before, the particles are united through springs. So at the end, we can use them as a way to do a form finding within structures. As our partners talked before about the optimization of forms, we can use this system to optimize the form finding of a structure. Let's say, so for example, here and here, and in terms of optimization, we talk about the resources and the best way they divide the forces that work within, so it sustains itself. And yeah, this would be an application of the of this particle spring system, which is the Bayer-Argenine Leverkusen. So the main idea of this structure is to reduce it as to reduce it that sustains, but at the same time that it functions within what it's for. So now we're gonna jump into the plugins. So we're gonna show you these 3 plugins, and I will give it the word to Yunus.
Yeah. So for the plugins regarding particle systems, we'll be considering 3 of them. So first is FlexHopper, and then Stellar 3D and Kangaroo. Starting with FlexHopper. So this plugin is based on NVIDIA Flex, which is a particle-based simulation engine for physics, and it uses like GPU with CUDA, so it's a parallel solver. So in that sense, it performs more efficiently in complex scenarios. And some of the basic simulations in conjunction with particles are rigid and soft bodies, fluid simulations, mass spring systems, inflatables, or the combination of these. Next slide. So the main components that constitute the FlexHopper is firstly the Flex Engine component, which is the core of the plugin, which combines the scene information and the parameters and the other simulation-specific parameters into the core of the algorithm. And the second most important component is the scene component, which specifies the type of simulation we're doing. So it could be a particle-based simulation, which most of the time we're doing, but it could also be rigid bodies, or we can combine different type of components into this scene component. And of course, to specify different types of parameters, we have a specific component called parameters, which we specify the gravity or the viscosity if you're doing the fluid simulation, or the wind or drag. Yeah. Next slide. So as for some showcase, so we see here a particle and rigid body collision simulation. So the rigid bodies are the cubes, and with FlexHopper, there is a built-in support for collision, so we can specify the rest distance or the collision distance between particle and the rigid body. Next slide. Another showcase is the fluid simulation, which we once showed before. So here we are using a method called position-based fluids, which is built in FlexHopper. On the left, we can see an aquarium-like scene, and on the right, we can see a fountain with obstacles. Next slide. Yeah, and finally, we have a mass spring system with self-collision. So we have 2 springs, and how this is achieved is with the springs component. So as I mentioned before, we have a scene component, and the type of simulation connects to this scene component. So one of them could be a springs component. So we specify the springs in the inputs, and the springs could be particles, which we can generate with points. Yeah, so we can take a look at the next plugin. Next slide. Yeah, the next plugin is the Stellar 3D. So the FlexHopper plugin was mostly based for physics simulations, but with Stellar 3D, it's not necessarily for physics simulations, but it also encompasses like multi-agent systems, and basically simulates the individual behavior of the particles within the population. So in this plugin, each particle is actually called a star and has the name of the plugin. We can show some main components. Next slide. So yeah, the star, as we mentioned, the star component is the plugin. So we make stars from the points, as in we are making particles from the points, and we can specify the lifespan, of course, which is a native specification for particles. And so then what we can do is to enforce like different types of simulations. We can enforce different types of forces, like the arrival force or the seeking force, and these forces are what keeps a particle in a population coherent or maybe dispersed from the population, as we will see in the showcase. Yeah, so the first showcase is the seeking force component. Here, what we do is we build a point and a target pair. So the points are the particles themselves, and the targets here are the curves that we built by specifying the text. Yeah, and we can see the simulation. Next showcase. So here we simulate the cellular growth using the reproductive age component. In which case, what this component does is it generates new particles from the existing particles. And how we achieve the 3D look is we use another plugin called Dendro, which generates volumes from the curves, but it's not really necessarily relevant to the particle framework, so I didn't mention it. Yeah, next framework. Next. So yeah, as the final showcase, we have the flow force components. So here, what happens is we have a gravity, and the flow force basically keeps crowd intact, so it doesn't disperse. So that way we can see a flocking sort of behavior. Yeah. So yeah, next slide. Yeah, for the third plugin, we have a Kangaroo plugin, so which many of you may be familiar because it comes built in with Rhino. So this plugin is not necessarily for particles, but nevertheless, it's useful for the particle systems because it sort of subsumes the particle systems, and it's generally used for meshes. But for example, we can do particle simulations because in a way those generated meshes use particles, and this this plugin is not necessarily for physics simulations, but general type of simulations and optimizations. So for that reason, we have a main component called bouncy solver, or no, previous. We have a bouncy solver and soft and hard solver component, which is the heart of the plugin. So what we do is we generate different type of constraints and we connect this to the goal object inputs of the solver components, and that way we can have like more flexibility in terms of the type of simulations we are making. Yeah, next slide. So as a showcase, we can generate a simple rigid body simulation made out of spheres. So this is kind of like a particle-based behavior. So here, what we're doing is we're visualizing spheres as particles, but usually in real-world scenarios, of course, doing this would be inefficient. So yeah, next slide, I'll show you more details. Yeah, for example, here we have a class simulation. So what happens here is we basically have a mesh, and we use the built-in component called the wind component, and this component generates the class simulation. But underneath, actually, what happens is we have these mesh is actually deconstructed into particles, and as Juan mentioned earlier, we are basically we're basically going from the particles and to the upper hierarchy. So the mass spring-based systems are acting on the particles themselves, not the actual entire mesh. Yeah. So next slide. So finally, for the comparison of these different plugins, so we can just summarize it. So we see that for particle support, we see the Flex software is already built in for particles. And for Stella 3D, we have components called stars, which is basically particles. But Kangaroo is not necessarily specifically for particles, but it's still useful nonetheless. The scope of these plugins are, as we saw, the FlexUpper is used for particle-based physics simulations. For Stella 3D, we have particle behaviors, particle simulations again, but with in the context of multi-agent systems or the, I guess, intelligence systems. And for the Kangaroo, yeah, we don't, the scope is much more general here. We are solving general simulations or the constraint solving or the optimizations. The main components are, yeah, the Flex engine, which is a single component in the FlexUpper ecosystem. So yeah, and in the Stella 3D, we don't have a main component, so we are basically building simulations from using various components in the Stella 3D plugin, but there is no single component. And in Kangaroo, what we do is, since we're solving a given constraint optimization problem, we just have a single solver. So then, following this, the extensibility-wise, we expect the FlexUpper to be the lowest in the list, because so it's not really extensible, because we're just using a single plugin, and we're just using the functionalities provided us by the FlexUpper plugins. But nonetheless, they are each of these components are efficient. So like the fluid solver or the rigid body solver is efficient, and because they each use the parallelization of the GPU. For Stella 3D, it's the second in the list. So since there is no main component, we can mix and match different type of components in this framework. And of course, in the Kangaroo, since it's much more general scope, we can combine different type of simulations and optimization problems along with the other applications to particle systems. Yeah.
And I'll start to introduce the multi-agent system. A multi-agent system is a mathematical model of a system that is composed of interacting intelligent agents within a shared environment. Instead of creating an environment and then letting the particles passively accept the influence of the environment, like the particle system we have just talked about, the central goal of a multi-agent system is to develop intelligent and autonomous agent. Different from a simple particle, an intelligent agent is an autonomous entity that is able to function and interact with a certain environment. After the agent perceives the environment, it will deliberate the input signals and then perform a range of actions to potentially change the status of the environment. Next slide, please. A multi-agent system has three main characteristics. First is decentralization. It means that there is no controller that dictates the action of a single agent, which means the agents coordinate with each other and observing others' behaviors for implementing certain system policies or constraints. The second rule is autonomy. It means that the agent is autonomous. They are solely good at solving problems or trying to receiving higher rewards without caring about the benefits of other agents. And the third is local view. It means that each agent typically does not have a full picture of the environment of any given time. They are making decisions based on their own vision. Next slide, please. Since the agents are the crucial part of the multi-agent system, they can be divided into three categories. The first is passive agent. It means that these agents have no certain goals like obstacles or key in a maze. These agents have like given physical properties and they can perform simulations. And the second one is active agents. It means that these agents have certain goals to complete, and they are self-organized and self-directed. They are able to taking actions according to the environment. And the third one is cognitive agents, and they can also be called learning agents as well. They receive the feedback from of the performance of other agents, and they can set up learning goals for themselves. Simply put, they can just communicate with other agents and design experiments for them. And as you can see, multi-agent systems emphasize the joint behaviors of agents within autonomy and the complexities arising from the interactions between them. So their working method can be defined into two ways: cooperation and competition. In cooperative systems, the agents pursue a common goal and they can expect benevolent intentions from the other agents. But in a competitive system, the agents have non-aligned goals and individual agents seek only to maximize their own gains. The fundamental distinction between these two systems is to set the goal of maximization of a group utility or maximizing the agent's own utility. Next slide, please. Compared with the particle system with passive particles, the multi-agent system tends to use intelligent agents to calculate the result by the communication. In short, in the multi-agent system, more efforts are devoted to setting the agent's properties and defining the rules of negotiation between the agents, and they can do far more than just a pure simulation. Next slide, please. As you can expect, in the field of computer science, the multi-agent system have many applications that are close to artificial intelligence. The most obvious is the simulating swarm intelligence. But what is swarm intelligence? Swarm intelligence is the collective behavior of decentralized and self-organized system, like a swarm of bees. In a swarm system, random interactions between agents lead to the emergence of intelligent global behavior, but it's unknown to the individual agents. An example of swarm intelligence is BOID, which simulates the flocking behavior of birds. The complexity of this system arises from the interaction of individual agents following a set of simple rules, such as separation, alignment, and cohesion. And there are also two applications in the field of machine learning: reinforced learning and multi-agent learning. Next slide, please. Multi-agent system is widely used in the field of architecture. The most common application is to abstract people, structure, or city elements into an agent and then analyze their movements to predict their future development. And in recent years, interactive architecture has also gradually emerged. That means the elements in architecture can respond to people's behavior, just like the green light in the atrium in the picture. Next slide, please. This is a specific example of how multi-agent systems simulate the pedestrian. The movement of a man is simulated by applying forces on a moving agent. The components are gate, target, and obstacles. Some targets of interest will also be set on the way, so the order of traveling through these targets are not specified. It only depends on the vision of each agent. The motion of the agent, next slide, please. The motion of the agent is based on the physical engine. The influence from the other components will be in the form of forces applied on them, so that the acceleration and the velocity can be calculated. And there is also a repulsion to avoid collision. And the attractive force will create several stops for agent and finally leading it to its destination. Next slide, please. And the mechanism of the environment is to calculate a shortest route from obstacle outline. That means the particles will move along the lines if they have not been influenced by the forces we have mentioned. And as you can see on the right side, it shows a simulation of customers entering a store. Next, please. Another example is Cloud Pergola, one of the pavilions at the 2018 Venice Biennale. Based on the multi-agent system, it mathematically captures the complexity of a cloud formation and calculates the dynamic mechanical relationship between these agents. Next, please. There are actually many other applications in other areas based on multi-agent system. As you can see on the right side, the first one is a simulation of cell growth based on a multi-agent system. When the agent density is increased to a high enough level, the neighboring agents will combine and form larger cells. That means the agents in a multi-agent system can not only move, but also merge or change according to the specific rules. And the second example below is a multi-agent system in form of robots. They can move systematically according to the light level of the surrounding, and they can also interact with each other to form specific graphics.
So next, I will introduce plugins related to multi-agent systems. I have found a number of plugins that are relevant, some with a complex and varied functionality, and others are specific to particular functions. For example, Pedism. It is a pedestrian path simulation plugin, and Hawk is a plugin that simulates the range of vision and the parts of people in the buildings. So next time. Firstly, I introduce Crealia, an agent-based plugin for designers. It can simulate cluster effects by analyzing the behavior of creatures in nature. This plugin is feature-rich and can simulate various behaviors in combination with setting conditions. In the field of architecture, it can simulate the evacuation of crowds from buildings and optimize building space. So, and it also can simulate architectural bionic structures. So next one, please. So here are all the components of this plugin. I have marked a few basic and core components with Redbox. So next slide, please. So this is the core building steps for this plugins. So this includes firstly that you should create the smart particles. Secondly, create the particle emitter. Third, create the simulation environment. Fourth, simulate the engine. And the fifth, you should do behavioral feedback iterations. So next slide, please. So this is some simulations I found that other designers do, such as path flowing, rainfall simulation and analyze, and foam finding. So next slide. The second plugin I found was Fezarian. This plugin is similar to the ant colony algorithm, which is a probabilistic algorithm used to find optimal paths. So the Fezarian plugin simulates the way slim bacteria plan optimal paths. So this is a design technique that can be applied to both large-scale urban planning and the small-scale spatial floor optimization in building. So next slide, please. So again, I have marked the basic and the core components in Redbox. So next slide. This is also the core building process steps for this plugin. So the general idea is to specify the a few points in a space as particle emitters, then a few points as food ends or food endpoints, and then generate particles through the main simulator and connect the particle into curves, and finally use the length of curves as a basic for giving the curve a color. So in addition, you can place obstacles in the space to make it more realistic. So here is different from the former plugin, but almost the components is similar. The special one is a timer operator, because this simulation process varies over time. So next. So here are some simulations that have been done with the plugins, such as simulate spatial networks and the form finding. So next. So the last plugin is Qulaba. So the application scenario is based similar to the previously mentioned plugins, but this is a processing-based program. So it also handles the data and visualization. And next. So this is a diagram of a dynamic simulation logic of this program plugin. So the red part are the possible agent behaviors, such as noise behaviors and clustering behavior. The gray part, gray part is the target or the destination of the behavior. The green part is the setting control conditions. So the blue part is the output or the geometry. So next. So here you can see the some simulation results. On the left is called octree behavior for mounting agent optimization. So on the right is a simulation of noise behavior. Yeah. Okay. Next. So finally, I asked some of my friends who had used these plugins so many times to rank them in terms of four aspects: the ease of the use, richness of application scenarios, and efficiency and visual performance. So firstly, in terms of ease of use, Physarion is the easiest to use, and it is relatively easy to get a result what you want. In Qulaba is the most difficult to get started with, because it's based on processing for simulation, and it is less controllable. So make it a more difficult to for people who have not a basic understanding of processing. So secondly, in terms of richness of application scenarios, Qualia can do different simulations, almost all particle related simulations. However, Physarion is more limited in terms of its function, in terms of its functionality, as it can only simulate ant colony effects. So Qulaba, because it calls existing package, so requires programming. If you need to simulate more situations, you should write some processing by yourself. So certainly, as you can see from the showcase I showed before, Qulaba gives the best visual effects. It also has the best runtime efficiency because it calls on existing packages. So Quelia was put last because it has to deal with a lot of data and it's very efficient. So finally, in terms of simulation results, Quelia has the best simulation results. Yeah, that is all. Thank you.
So we just left a link on the chat so we can interact a bit with the fluid simulations or visualization for later on or now. So do you have any questions?
Actually, I have a small question. There was the plugin Kangaroo, and you said that there is a built-in component like wind, but is it a random wind or we can use some information like for the weather file? So for a specific place, so we can simulate not only the wind, but also the movement or the clothing simulation.
I believe you can specify the direction and the magnitude of the winds. But I haven't checked it much thoroughly.
Thank you.
Have you tested all the plugins you showed us?
Yeah. Do you mean the Kangaroo and?
Yeah, all there was such a mess in a positive sense. So, did you have the time to check them, or was it kind of a mix? So some of them you tested, some of them you knew already.
I've checked the FlexHopper and the Stellar 3D plugins kind of thoroughly, but I haven't looked into Kangaroo yet. Kangaroo much because it's more general purpose plugin, and
Okay.
I only looked at basic applications to particles, and I saw the like the rigid body simulations and the cloud simulations. So yeah.
Cool. Just one thing. Was very good. Thank you very much. I have two ideas, or one idea. Maybe we can do some kind of Excel list or table in the Moodle where each group can put in the plugins, just as a name, maybe a name and a link, and the general topic. So we have all a new overview, and we don't have to go through the whole presentations each time when we search for something, because it's, I don't know, I think we have now 30, 40 plugins so on to seen today. So I think it would help if we have an overview. If this is not possible, Elida, in Moodle, then we do an Excel and we upload it to Moodle.
Yeah, that makes sense.
But I think this helps a lot. Otherwise, everybody's checking the presentations, the searching, and all that.
Yeah, I'm not sure if Moodle would work, but yeah, we can find a solution.
Excellent. I think Excel is even better. The other question is, we have one group left. Are you still fit that we do it today? It would be good if we can do it today, but we have just, it's nearly 1 o'clock, so, and it was a lot of input. If we all say, hey, no, it was so much input and have to go to another course, then we can shift it to next week and we start at the beginning with this presentation, if that's also okay for the group. Then and after that we do the workshop. So I would say you can decide what you prefer. Maybe first
I think we can.
Group. No, then start.
I think we can make it today because we have a video, and if we can't really understand, we can watch it later another time.
Yeah. We can do it today, I think. I mean, I'm with the others from my group also fine with it doing today.
Yeah, and if someone.
Yeah, I think they're all here, so I think.
Okay, then we do that. I also have to watch the video because I have a workshop the whole afternoon from 1 o'clock on. But
I'm not in the group, but I actually can't stay longer because I have a lecture at 1. So, but I think it's not like I can watch the presentation on my own in Moodle. So
yeah,
The
that's
people,
a very good point.
the people who are presenting, can you do it now?
Yeah, Michael, just one thing. If you want, I have the whole day is a meeting, or not. I have the workshop. But if you want, we can talk on Monday or Tuesday. What you said yesterday, because
Tuesday.
I really like the idea, and I would like to. I think maybe I can help you.
Tuesday would be good for me. Dienstag.
Ja, dann
Ich kann auch noch
just
eine
write
E-Mail
an
schreiben,
email.
deswegen.
Ja,
Genau.
Tuesday, Dienstagnachmittag klingt gut.
Ja.
Ab 2.
Passt. Dann schreib mir nochmal eine E-Mail oder sowas, dann können wir nochmal genau machen.
Super.
Oder wir sagen genau 2, das wäre auch sehr gut.
Ja. Schreib einfach.
Mache ich.
Okay, now the last group.
Maybe just a general question before. He's gone already. No. Yeah, before everyone goes, for the next week, we have this workshop, don't we?
Yeah.
Should we prepare some general concept already for the? No. Okay.
What you can bring in next week is, I think everybody will somehow have maybe some ideas in his mind already. This is good if you bring them, but you don't need to present them. We will try to do 2 or 3 steps with different methods and methodologies, just to figure out what could be possible.
Okay,
Normally
great.
we spread out and make a huge space of possibilities, and then we try to pick out some of them.
Okay, perfect. Thanks.
Yeah, and I think today's presentations were really inspiring. So some of you probably already have an idea what could be done.
All right. I think then I start with the presentation. We're the last one. We talk about interface and visualizations, and I'm here together with Hyong, Ke, and Yuhong. I hope it is pronounced right. And yes, next please. So firstly, what is a user interface, or like an interface? In user interface is typically like the visual part, which how the user can interact with a specific application or software. So it's like the information, the displayed information. That's one. Then we go to like, why is it important? Like first and foremost, like almost every user judged an application or software more on the interface or how it is interacting with the user than its actual functionality. So if the application is really good at interface functionality, but the user interface is bad, then it gets bad responses from the users. Also, like if it's bad in poorly designed, you can make catastrophic errors more easily. And if you have a good user interface, it's also eased learning curve, and also like it's easier to use, which is like typically known. Next one, please. There are 3 main types, you could say, of user interfaces. You have the command language on the left, just like the typical IT or programming. If you think of something, then you always think of like the command language type user interface. Then you have like a menus interface. This also goes a little bit more already into graphical user interface, but a little bit of subtype, where you have like in a typical old Windows fashion, like you have the file path and you have like different menus where you can select from. And then the graphical user interface, it's like really where you have like also like you go deeper into the graphical user interface later on, and it's really heavily based on the graphic or like visualization part. Next one, please. So the graphical user interface, or GUI, it relies much more heavily on the mouse, and it has like advantages like you need less expert knowledge because like everything is more easily accessible, or like it's easier to navigate. The problems are that you have like decreased options, you can't customizable it, and it's maybe a little bit slower for experienced users, but it's still like for inexperienced users really good. And also like for us architects, it's actually really important that as we are designing or we are creative, we need to like an intuitive user interface that we can achieve like bring our ideas into the software, or are not like restricted by the software. Next one. So they're like from, according to Larry Constantine and Lucy Lockwood in their usage-centered design, they present like principles of the interface design. There's the structure principle. This is just like to have a really organized interface, which has like meaningful, useful ways and putting related things together. The simplicity principle is just really that it's maybe providing good shortcuts or making simple and common tasks easy. In the visibility principle, the design should need to make the materials for a given task visible and don't distract with unneeded information or other parts. Then the feedback principle is actually just like that you get a kind of feedback if you make something wrong, like an error, or that you have like a state of condition which informs you that you have like done something. Could be noise, could be also like pop-up or something as well. The tolerance principle is actually that you are allowed to maybe redo and undo, and it also like that you have like in preventing of errors whenever it's possible. Like in Grasshopper, it's also like if you have like different data types, sometimes you don't need to know exactly the specific data type. So it also like gets, it's like a logic-based interface. And the reuse principle that is you have like the same principle again, or the same task you want to do. It's like not something that you need to rethink or have another interface part. Next one, please. So now to go to a little bit also for data visualization, and the others are talking about the plugins, a little bit about later on. So about visualization, I just started with the what is data visualization, because like in every presentation in the industry nowadays, we have a lot of big data, a lot of data, and to understand this data is really significant to show this data in a graphical way, because like you have an advantage of like convincing the other participants. Next one, please. So with data visualization, we often talk about the graphical representation of it. And there you have like the typical parts like your charts, graphs, and maps. Later, I will also like show a little bit of architecture where we have like a combination of all. Next one, please. The importance is actually, it's really logic, like it's easily graspable information. You can see established relationships a lot better. You can share it with other people who can understand it better. It can also be an interactive visualization, and you can also like make it personalized or to your what you're like personally feel is more important, like you can focus on this. Next one, please. So this is like also the benefits, which are a little bit the same with the last file, but it's like make it it's more efficient, increase the speed for decision making. It can like identify errors more easily. You can have also like real-time information if you have the data therefore. You can also like maybe tell a little bit of story to your audience to convince them. You can have insights into business or like into the data, like into the what is like in like if you are going in the right direction, like you can make decisions better. And yes, next one, please. If you want to visualize something, you need to know like a few techniques. Like you always need to know the target audience for your visualization, because like if you have different audiences, you need also different visualizations. Then we need to have a specific goal, which type of data I want to present. Then I can choose the appropriate type of visualization, like the graph or chart. And then we need to have like the context also. We can use maybe colors, we can use others stuff like maps or something which presents it a little bit better. And it's also there are a lot of different tools we can use, and later maybe in Grasshopper we can go deeper. Next one. And in architecture, why do we use it? Like this is a lot of topics which should be or could be used for this data visualization. Like if you have maybe a look later on it's just like all the different parts of architecture can be used for we can use visualizations to better present them, like in housing, topology, geography, environment, scale, and so on. Next one. So a short overview about the main presentation of data are bar charts. We all know it, pie charts, line charts, and area charts. And like in architecture, we have like mostly a combination of all in the maps, and which is also really interesting. I show in the next pages, like all these basic types are connected. Like the bar charts, it's like shows a comparison. A pie chart shows also a comparison, but in a different way. Line chart has a time over it, like also a bar chart has also the time period, and an area chart is like used to show volumes in a combination also with a little bit of a line chart. Then we have like scatter plots. It's also a little bit like a line chart with the time aspect. And if you then maybe have the bubble chart, you can see if you have a line chart, scatter plots, and the bubble chart, you have like a second layer of input data, because there you can maybe also see the volume. And also, like we already see from Ladybug or something, they always use heat maps to present data, because it's actually really useful to show it in a graphical way. Next, please. So this is like a few examples. On the left, you see New York, where it is shown that how many cars are actually driving on. So it's also really visible way how many, like how the verkehr ist. On the second, you see the heat maps, which is like temperature, like from a whole year in a place. And also really important is that you always have like a scalar right next to it to show really from which point to go to which point, like from 0 degree to 34 degree, or from -10 degree to 50 degree, because like then if you have like a heat map with colors, and it can be a lot of misleading if you have a scalar which is like wrong calibrated actually. The next to the right, you see, no, not the next slide. So here you see like a bubble diagram with a site map with the red points, like if bigger points show more like people. The next is the wind study like we've seen earlier. Next slide, please. And here we also like have like a site analysis actually with like a lot of different graphical types combined together. Next one. And also a part of visualization is actually like how you can like render or visualize your project in the end.
And then I want to introduce something about plugins. First is Human UI. Human UI is a plugin for interface and visualization. And for example, when you want to show your project with some designers or clients who have no understanding of Grasshopper, Human UI is a good tool, and it can transfer the complex plugins like the left picture to some visualized sliders, text boxes, pull-down menus, and even 3D views in a single window, like the right picture. And next slide, please. And these are plugins for Human UI. First, the containers. You can use these plugins to adjust the data arrangement in the window. And for the elements, you can create some sliders or text boxes in the window. And you can also add some graphs and charts to analyze the data. And this main components, you can create window and set some window properties from here. And also you can add some output plugins. And I want to show you a video to show how it works. You can first create a window which connect to a boolean toggle, and you can change it to true. And here are some parameters that you can change. For example, the form parameters, floor numbers, and floor to floor height. And you can see that the 3D view will be changed at the same time. It's a bit slow. And you can see that the charts will also be changed. So that is so visualized for other people to see how the building looks like. And I think it's a very useful tool to communicate with other people. But I think this plugin should be improved, and sometimes when you change the name of the number sliders, it won't be changed in the window at the same time. So in this case, you must delete the slider and then create a new slider with the right name. Yeah, and next please. And then is another plugin, Human. And Human can extend the Grasshopper's ability to create and reference geometry, including light blocks and text objects. For example, you can see the random display mode. In Grasshopper, if you give a color to a geometry, it won't be displayed in Rhino after you bake that. But in Human, you can create some attributes for the object, such as material or simple color, and then that will be displayed after baking and select the right picture. Next, please. And there are some plugins for Human. Object creation, display, document information, document modifications, miscellaneous, reference, and texture mapping. And at the bottom is some reference guides from the Human website. And in my opinion, it's quite useful to visualize the geometry. But if you want to get some analyze graphics through this object or geometry, you also need to combine those geometry with other software, for example, Adobe Illustrator, and that is not so easy to create this analyze graphics. And next, please.
Yeah, I would like to introduce two plugins that can connect to different design environments and enable transformation. And the plugins are like bridges that enable different and very practical users to help the designers to design and modify better and faster. And this is the Archicad Grasshopper Live Connections. It is made by Graphisoft. Yeah, and it enables Archicad users both Mac and Windows to import and export and link to Rhino models through the 3DM format without additional download, and to seamlessly to work with Rhino through the connection. And with familiar nodes in Grasshopper, it's easy to create native Archicad BIM elements to automate and simplify common and complex tasks. And this is a very practical interface plugin, usually designed and adjusted in Archicad or Rhino, and the real-time transformation reduces the workload and enables more possibilities. And to explain the workflow, I have chosen two options. operations as examples. Next, please. And yeah, one function is simple deconstruction. And this allows designers to maintain the basic design logic in BIM, such as the base geometry of the building, and extend that with intelligent design details that follow changes in the core design. And next, please. And at the design further, our architects create the first mass of the building volumes at Archicad, and then later add the data of walls, roofs, slabs, and windows on doors, and then add the new mover shape to the code using the 3D window of Archicad, and open the grasshopper through this deconstruction function to create the models with many details based on the conceptual math model. Yeah, and next. And we receive the no, it's not my slide. No. And we receive the BIM model. And next, please. If we want to do some adjustment when the geometry of the MOFO model was modified, and the associate BIM model will update automatically, but without it, it will take a lot of time. Next, please. And another function is to create a free-form shading device for a multi-story building. Designers may use a truly unique parametric free-form design in a professional building information modeling environment. Yeah, due to the connection. Next, please. And create. Okay. Okay. Sorry. Okay. Next is the Follogram. Another plugin is Follogram. This is a very interesting plugin for interface and visualization in the same time, and useful the design, share, and create a mixed reality. And the visualization of Follogram is powerful, and it can create interactive, immersive mixed reality presentations from existing Rhino and Grasshopper models, and design and construction with mixed reality are practiced a lot for the classroom, studio, and workshop. People can connect Rhino and Grasshopper models to other devices such as iPad, mobile phone, and VR devices to see the holographic model mixed the reality. And man can view and share the models with unlimited HoloLens over the VR glass, and mobile diver devices over Wi-Fi with one click, and edit geometry layers and the Grasshopper parameters on mobile and HoloLens in real time, and it helps to communicate with others and make design decisions faster. Next, please. And how it works. Follogram connects mixed reality devices to Rhino in real time, and then detect interactions and build user interfaces, and then they can create mixed reality solutions in Grasshopper. We can see the pictures. People can modify the parameters through the phone. So through the VR equipment, can see the model to fix the nodes. And the last pictures show the manual adjustment of the angle of the complex installations in the building process. And currently used in installations and small buildings, it is not widely used due to the high cost and the lack of some stability of manual adjustment. However, it is very interesting and excellent way to explore and innovate it for the design, and it offers more possibilities for creation. Thank you. Next, please.
Now, Mandarin's functions is mainly data and data visualization. It is mainly used to make a bar chart, picture, or the other chart. It is easy to change the color, but the type of the graph is not too many. And here is a client. And here is a small example for data and data visualization. The source of the data can direct in Grasshopper create, or we can put the under data in the Grasshopper. And here can we choose which type of graph we want. And here can we adjust the graph performance. Yeah, here is the picture. And the second khaki bomb is the connect the OpenStreet data for OpenStreetMap and Grasshopper. We can quickly to create a plan and download the OpenStreetMap data. And here it is an example. Here is our Universität. And explore the data for OpenStreet and to put in the Grasshopper. And here we can choose which element we want and we didn't want. And for example, here is the building scrap, and here is the 3D models. If there are some high information, and here is a way. So that's all. Thank you.
Any questions, or are everyone sleeping?
And can we make a heat map with some of these plugins?
So if you want to make a heat map especially from one plugin, or because it was difficult because a lot of plugins always have their heat maps inside their normal structure. So Ladybug, for example, has a heat map for their weather data. So there you wouldn't need a specific plugin for that, actually.
Thank you.
Hope that helped.
One question still, a short one.
the last slide with a map, extracted all the information from. Is there a like specific source of map that we have to use in order to create those street networks and stuff?
So we get the data from the website OpenStreet, if you mean that.
Okay.
Mhm.
Okay. So which kind of
Oh, I think we couldn't hear you.
Oh, okay. No, it's fine.
Can you repeat the question?
No, I was just wondering from the OpenStreetMap, which kind of format are you using in this case in order to extract those, in order to work with this plugin?
I think they just you need to just a file path actually of the OpenStreetMap, and then you can just if you see it on the screen there, it's like the C++ and then backslash. You just need to insert the file path there. Then you need to predefine an OpenStreetMap in the file path. I think your extent.
Wow. Yeah, that's really cool. Thank you.
Also another one which is just ELK that you can also have really easily create streets and something like that.
Maybe you can stop sharing your screen. Okay, if no one else have any questions left, before we go, I want to thank you everyone for your extensive research and inspiring presentations. While uploading everything to Moodle, please don't forget to add your resources. And if you think that something is very relevant or interesting, but you didn't present it, you can also add it, because I think later on other people who will use that concept will be very helpful. Yeah.
Could you maybe upload the slides from the first lecture because of the scenario with the population density, etc.?
You mean for the example projects?
Yeah, just the slides of the first lecture.
Yeah, of course. But also you can check the Architecture Informatics website. There's also some projects from previous years, and they can be also helpful. Okay,
I have one question according to the project that we have to do. So you said that we can do it alone or in groups, but is there any limitation on how many people can form one group, or maybe is there any difference? Because I mean, it's much more job when you are doing it alone, and much less if you are doing this in a group of 6 people. So.
But I think 6 people might be too much. I'm not sure if Gerhard has some specific number in his mind, but I think like 3-4 people maximum would be ideal. And if you're alone and the other group has 4 people, of course the expectation or the workload would be different. So don't worry about it. Does anyone else have any questions?